So there is one more concern that we have when we calculate the dynamics of harmonic oscillator, and that is how to really express it in space. So how to calculate the eigenstates of the harmonic oscillator in space. This seems to be quite easy because they can be found in the literature very easily. So psi and q is actually some normalization factor depending on n. I will write out what it is, multiplied by a Hermite polynomial of the nth order and multiplied by the minus q square divided by 2. That's for our dimensionless case. Here n is 1 over square root of pi n factorial 2 to the power of n, and the Hermitian polynomial is best expressed as minus 1 to the nth power e to the q square multiplied by now nth derivative of the e to the power of minus q square. So you can ask, how the hell am I going to program nth derivative of this thing in a program? How am I actually treat n factorial for large numbers so that it doesn't explode? So there are many problems with this definition, and I will show you one simple way how we construct all these things here without having to go into factorials and without having to calculate any derivatives or whatsoever. We will only need the first wave function psi 0, which is 1 over pi to the fourth root of pi e to the power of minus q squared divided by 2. You can try out that this is indeed a solution of the Schrödinger equation. So maybe let's write the Schrödinger equation here. Schrödinger equation in space for us looks now like this. This was Hamiltonian. There was a square of the impulse or momentum plus q square, and this now should be, so we should act with this on this q, and we should get the ground state energy and the q back. So we will be looking here at the left hand side first, which is this, and now second derivative of this thing. So it's basically minus d, it's the minus derivative. Here we take the plus derivative, so it's 1 over p fourth root of it minus q. That's what we get by taking derivative of this, minus q square e to the power of q square divided by 2. So that's when we acted with this for the first time, plus we have h bar omega divided by 2 q square e to the power of minus q square divided by 2. And we continue with the left hand side. So this is still the left hand side of everything. We have to perform one more derivative. So this is again h, let's go back to the original color, h bar omega divided by 2. Now the minuses get eaten first. The time derivative has to be done, the space derivative has to be done according to the chain rule. So this is, and here we forgot 1 over p 1 over 4. So this is 1 over pi 1 over 4. Here is the derivative of this, which gives me 1, so it's e to the power of minus q squared divided by 2, plus this whole thing again, and now I'm taking a derivative of this part, which gives me minus q again. So it's altogether a minus q square e to the power of minus q square divided by 2, plus 1 over pi 1 over 4 here, omega to the square e to the power minus q square divided by 2, which is, now I can see that I have minus q square here plus q square. This goes away like this, and I'm getting just h bar omega multiplied by q by psi 0 q. So that gives me also that the E0 is h bar omega divided by 2, which is correct. It's all right. So this is my initial wave function, and I have no doubt about, well, the ground state wave function, and I have no doubt about that. Now I said I need just that, which is really true, because out of this wave function I can create everything else by creation operator. For example, I can assume this. So the creation operator is, I'm not sure if we have written before this version of it, but it's basically this. It's the q coordinate minus I, the p operator. So it's like this. These are all operators. This means that, or maybe there's plus here. There's plus here. So this means in our representation, it's gonna be q, not the q operator, but q minus derivative according to the q. So this is the creation operator. And I also know that the n plus 1 state, which I might be looking for, is just the n 1 over square root of n plus 1 creation operator acting on n. So by this token I should be able for any given n get the n plus 1. So if I start from 0, I can continue farther. Now this is not yet very helpful, but the second thing here is already quite helpful. So I can write in the I can now write in the coordinate representation the following. I can write the psi n plus 1 q, that's this, is equal, and now using this definition, it's 1 over square root of 2 n plus 1 here, q minus time derivative on psi n q. And unfortunately this is not very helpful, because here I have the time derivative and I don't know how to work with it. I mean, at least not in the computer. This is not a recursive formula that I have promised myself here, but there is a trick how I can get to the recursive formula. So this time derivative, if I just put I in front of it, gives me the p operator, which means that the time derivative itself is just I p operator, and the p operator can be expressed by the creation and annihilation operator again. So because p is equal I divided by h bar divided by square root of 2 a dagger minus a, then it means that the derivative of q is minus 1 over square root of 2 a dagger minus a. So we are now in a different, well, in a position of writing out this time derivative, so the space derivative. So the space derivative in coordinate representation would look something like this, where, well, I don't know how to write the operators a dagger and a in the q representation, but I certainly know how they work. So they will give me here, this repeats, so this is square root of n plus 1 psi n plus 1 q, and the second one gives me minus square root of n psi n minus 1 q. That is the time the space derivative of psi n q can be written in terms of the psi n plus 1 and the psi n minus 1 q. So if I put it back into this expression here, I will get that psi n plus 1 q is equal to, now it's going to be a little bit messy, there is a square root of twice the n plus 1 q psi n q, that's from here, that's this q here, and now we will be adding what we've learned about the derivative according to q. So we will get plus, here will be square root of n plus 1 divided by 2 multiplied by 2n plus 1, so this immediately kills each other, psi n plus 1 q minus a square root of n 2 multiplied by 2 n plus 1 psi n minus 1 q. These don't kill each other, and we'll be getting to a preliminary result which says psi n plus 1 q is equal to 1 over square root of 2n plus 1 q psi n q plus 1/2 of psi n plus 1 q. That's, well, that's here, that's from here, minus 1/2 square root of n divided by n plus 1 psi n minus 1 q. And that is, so I take this to the left hand side, so I see there will be 1/2 of the psi plus 1, so I divide everything, so I multiply everything by 2, and I get the, well, actually the final result of this part, which is that psi n plus 1 can be written only in terms of the known, or if I continue iteratively from 0 using the known psi n q and psi n minus 1 q, psi n minus 1 q. So this is a formula which doesn't have, I mean, that's of course from experience, doesn't have the problem of dealing with factorials and so on. So also it works quite well if you start from 0. So if you want to calculate psi 1, the n is equal to 0, so you get here 0, you get square root of 2 q psi 0 q, and this guy you ignore. So this is how you get the first one, and then you continue second and so on. You can verify that the definition, of course we would have to find out also how these Hermitian operators look like, how these Hermitian polynomials look like, and everything. You can verify that this iterative formula actually is correct and works. And for calculating the spatial extent or the spatial form of the wave function, you really, using this, you really need just the form of the first wave function, which is very easy. It's just one Gaussian, nothing else. So I suppose now we have really everything in our hands to just program it in Octave and plot some nice evolving pictures that show how the harmonic oscillator evolves under quantum dynamics.